Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I'll be walking you through the chemistry course. In this particular lesson, we'll be considering the periodic table under the title Families of Elements. Periodic table, families of elements. And in this lesson, we'll look at the periodic table itself. We'll talk about electronic configuration. Then we'll look at groups and periods, and then periodicity of properties. Then we'll consider the groups, that is group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 0, or some people do call group 8. And then we'll talk about transition elements. Alright, let's talk about periodic table. So what do we mean when we talk about the periodic table? Of course, as learners in chemistry, periodic table is simply a table that contains elements of different types, elements arranged based on the number of atoms in their outermost shell. And like I said, it shows the number of atoms in the outermost shell and the number of shells which they do contain. The number of shells which they do contain and the number of electrons rather. Number of electrons in the outermost shell and number of shells they do contain. While the group shows the number of valence electrons, that is electrons in the outermost shell, the period shows the number of shells which they do contain. There's a law called the modern periodic law. It was proposed by Mendeleev in 1869. That's a modern periodic law, and the modern periodic law states that at regular intervals, the property of atoms, of elements, tend to become identical. That is, when you compare lithium and you compare it with sodium, you find similar traits. You find similarities between their behaviors, both physically and chemically. That is, their physical properties and their chemical properties tend to link together. So, what is the relationship between these properties? That's why we are going to take a look at the periodic table. About now, a periodic table will be shown on your screen. Now, on your periodic table, you will see, we say about 8 or more, actually more than 8 rows. That is, more than 8 columns rather. More than 8 columns, and you see about 5 different rows. Yes, the rows are the horizontals and the columns are the verticals. Now, if you observe, you see that in between we have the group 1, we have group 2, then we have one very long in between, then we have the group 3, and then the group 4, 2, and then the last particular one on that particular list is written group 0. Some people do classify it also as the group 8. So, each of these elements, if you see under group 1, we have hydrogen floating between group 1 and group 7, not really placed anywhere in particular, but then we see immediately after the hydrogen, we see lithium, and then under lithium, we see sodium, and the likes as that. Potassium follows immediately afterwards. Of course, we have the group 2 as well, and the group 3, the group 4, and the others like that. Basically, the periodic table simply shows us how atoms of different elements are being arranged. They are being arranged. And when we look at each period point, an extra shell has been added to the number of shells possessed by the atom. So when you're drawing the atomic structure, you have the introduction of a new shell with each particular period. Alright, before we go further, yes, like I said, periods are horizontals and the groups are vertical. But before we go any further, let's take a break, and in this break we'll have some questions displayed on your screen to test your knowledge, your understanding of what has been taught in this lesson so far. Please do well by answering them, and we'll see in a few. Welcome back. So, in this particular lesson, we've talked about the periodic table, and we mentioned some things about the groups and the periods. But let's talk more about the electronic configuration. The electronic configuration. So when we talk about electronic configuration, what do we mean? What are we referring to? Electronic configuration simply talks about the arrangement of the electrons in the shells. The arrangement of the electrons in the the shells. Now, in the shells can hold certain limits of electrons. We have certain limits of electrons that the shells can hold. In the first group, where we have the shell, let's say, take for instance helium. Of course, helium happens to be a group 0 element. It has 2 electrons in its outermost shell. So you see, of course, we talked about every atom to have a nucleus, or let's not indicate our nucleus as this. It has a nucleus, and then it has a shell. And this is what we have in the helium. It has a shell. Of course, in our let's take oxygen. Oxygen has 6 electrons. So, of course, it has the nucleus, which is a combination of a couple of protons and neutrons. Then it has a shell. This first shell can only accommodate 2 electrons, and it is known as the K shell. Is known as the K shell. After the K shell come the next shell that can accommodate a maximum of 8 electrons. It is known as the L shell. So on the L we have oxygen is 8, sorry. So it will have something like this. To have a structure something like this. So when we're talking about the electronic configuration, it does not necessarily mean to draw the cell, but how are the electrons distributed on the shell. So when we want to draw electronic configuration for helium now, we'll see hydrogen goes with H, which has just 1. Well, helium has 2, which is 2. Lithium has 3. The first shell can only accommodate 2, while the third one would, the second shell will accommodate the 1, and it will go like that till it gets to oxygen, where you have 2,6, and then it will go like that till you get to neon, where you have 2,8, which is a stable cell. The outermost shell at that particular point will be completely exhausted. It will be filled, and then we can go to substances such as sodium, where we see sodium with 11, which is 281, and from sodium it will keep increasing like that till it gets to argon, where we see 18, that's 288, and then it will keep increasing like that. So electronic configuration is simply we representing how the electrons are being arranged. Now the shells can be either K, L, M, N, O to indicate which of the periods. As the shell is increasing, the atomic size also is increasing. As the shell is increasing, the atomic size is increasing. Alright, let's talk about periodicity. Periodicity of some substance, of some properties. When we're talking about the periodicity, we're talking about the repetition of particular properties. Repetition of particular properties. That is, when you're observing, you notice that almost all the elements in group 1 have certain features common to them. If you take careful note, you observe that all the elements in group 1 are metals. That's to begin with. All the elements in group 1 are metals. Take a look at your periodic table right now. Yes. You see them? Lithium, sodium, you see potassium, and the rest of them. They are all metals. The same thing applies to elements in group 2. rather than they being just metals, they are another set of metals. So that's what we're talking about when we talk about the periodicity of certain properties. Now, how do we observe this periodicity? If you take about now, you'll be saying description of set. We'll talk about physical properties. We'll talk about the boiling point and the melting point temperatures of these substances. Generally, group 1 elements have very high boiling and melting points, and as it changes group and comes lower, this boiling and melting points begin to reduce. So if we take a look at the graph that is being displayed on our screen about now, we'll notice that the boiling points, of course, it changes. The same thing happens when we take a look at the temperature. When we also consider the ionizing energy. You observe that each of these graphs, you're looking at the ionizing energy graph right now. Each of these graphs, if you look at it very well, critically, you observe that it is changing. The shape of the graphs are identical. The shapes of the graphs are identical. Also, when you take a look at their chemical compositions, as in chemical properties, in terms of the chemical properties, you discover that group 1 elements have they can react with identical materials. They can perform, the rate at which they do react is identical to the rate identical to every member of the group. Same thing applies to group 2, is identical to that of the group. And those of group 5, group 6, group 7, they also react in identical manner. So this is what we talk about, this is what we are referring to when we're talking about periodicity of elements. So, having spoken about periodicity of elements, let's take a focus on group 1 elements. So, let's look at the group 1 elements. In group 1, we have a lot of interesting elements there, but for the sake of this particular lesson, we'll consider elements that fall between the first 20 elements, and we might not consider certain elements. What are the elements that fall in the first 20 elements for group 1? We have lithium, we have sodium, we have potassium. Well, it might interest you to know these elements are called the alkali metals. They are called the alkali metals. And this suggests that their oxides react with water to form bases. When you take their water and their oxides, they dissolve in water and they form bases which can take part in neutralization reaction when mixed with an acid. So we call them the alkali metals. And apart from calling them the alkali metals, they are all univalent. When we say they are univalent, it means that they have just one valence electron. One valence electron. That is, they have one electron in their outermost shell. While lithium has 2 shells, sodium has 3, and potassium has 4. So potassium has 4. So basically, these particular elements all react in certain ways. Now, all of them, I'll place our focus on sodium and potassium. So I'll take out the lithium. Now, both of them, both potassium and sodium, react vigorously with water. They react vigorously with water, and when they react with water, they liberate the hydrogen gas. So they react with water in the formula Na, let's say 2Na solid, reacts with cold water, and then you have something like Na2O plus hydrogen. Hydrogen gas will be given up. So we see this kind of chemical reaction coming up. They react with water and they liberate the hydrogen gas. Apart from them reacting with water to reacting with cold water, they react with cold water. Apart from them reacting vigorously with cold water, when you have their trioxonitrate salts and you heat it, they decompose. Their trioxonitrate 5 salts decompose. Sodium trioxonitrate 5 will be NaNO3. If you should pass it through a reaction called heating, if you should heat it, heating process, you have NaNO2 plus oxygen gas given up. Now that means you have 2 of this and 2 of this for the equation to be balanced. So when you heat their trioxo, that is sodium trioxonitrate 5, what you have is a decomposition which will result to the production of sodium dioxonitrate 3 salt, and oxygen gas would be liberated. So these are some of the basic chemical reactions which we do find the alkali metals, that is the group 1 elements, take part in. In group 2, we'll find elements as beryllium, magnesium rather, and calcium falling into the first 20 elements. We won't take beryllium into consideration. It is highly reactive, but this particular two, find out that they have similar traits as well. This particular group are known as the alkali earth metals. They're known as the alkali earth metals. We can find them in the natural state in nature, and also we'll find them in rich abundance in nature, mixed with certain components that they can be easily separated. Apart from that, they exist in the divalent state. The divalent state. This suggests that they have 2 valence electrons. They have 2 valence electrons. So these particular substances and these particular elements, when we react calcium with cold water, it reacts at a very, very slow rate. But when you heat up the water, the reaction process becomes faster. So when you react calcium with warm water or hot water, it reacts very, very fast. Now, if you react magnesium with hot water or cold water, it would not react. Magnesium only responds to steam. Yes, magnesium only reacts with steam. So, and the chemical reaction between either magnesium or calcium with water, that is either water or steam, respectively, will produce what is shown on the board. It will lead to the liberation of hydrogen gas. Hydrogen gas would be liberated. Of course, the base, of course, will be produced as well. When you also eat the trioxonitrate 5 compound of any of these particular group, you have it decomposing into the oxide of the particular element. The oxygen gas will be liberated, as well as the nitrogen 4 oxide would also be liberated. So the production of nitrogen 4 oxide, which is a brownish gas, it will be observed in that particular procedure. And also, if you heat up the trioxocarbonate 4 compound of these substances, they will produce the oxide as well as carbon 4 oxide. So in group 3, we have interesting elements such as boron and aluminium, but we have aluminium as our main focus because it is the most popular among all the group 3 elements. And of course, we have our aluminium. The oxide of aluminium exists in a very unique state. It is trivalent. It is trivalent, which means it has 3 outermost electrons. 3 outermost electrons. That is 3 electrons in the outermost shell. So, apart from the fact that it is trivalent, its oxide reacts. Its oxide reacts with both acids and bases to produce salt and water. When they react with bases, actually they produce complex salts. So we have the expression on the board. We have aluminum oxide reacting with tetraoxosulfate 6 acid, and we have salts and water produced. And when we have the same aluminum oxide react with sodium hydroxide, of course you add a little water so that the reaction can actually take place, because this needs to be diluted. Sodium hydroxide needs to be diluted. The reaction will result in the production of this particular complex salt, sodium aluminium hydroxide. So the complex salt will be produced. Also, when you take aluminium trioxonitrate 5 and you heat it a little, it naturally decomposes. In fact, even without heating, it decomposes to form the oxide of aluminium, oxygen, and of course a lot of the brown gas, nitrogen 4 oxide. That's the brown gas, nitrogen 4 oxide. We would have also tested what would have happened if we were to work with the carbonate, the trioxocarbonate of aluminium. But aluminium does not exist. It does not have a trioxocarbonate form. It does not have there is no such thing as aluminium trioxocarbonate trioxocarbonate 4. So we don't have the aluminium existing in the trioxocarbonate form. So that's basically what group 3 elements are about. So the group 4 elements now. Let's consider the group 4 elements. In group 4, we have carbon, that's carbon C, and we also have silicon. Yes, we have carbon, we have silicon. Carbon does not react with water. To note, of course, there are 4 valence electrons. There are 4 electrons in the outermost shell, and this makes them most of the time to react in what we like to describe as covalent bonds. They react most of the time in covalent bonds. Now, for both carbon and silicon, you can find them in having they have chances of having dioxide. They have chances of forming. They have chances of existing in their 2 states and in their 4 states. In their 2 states and in their 4 states. How do I mean by in their 2 states? You can have carbon 2 oxide, that's CO, and you can also have silicon 2 oxide, that's Si. In like manner, you can have carbon 4 oxide, CO2, and you can have silicon 4 oxide, which is SiO2. Alright, carbon does not react with water at all. Cold, hot, warm, anyhow you make it, it does not react. But when it comes to silicon, lead is Pb. These ones, they do react with water. Tin, yes, tin, S. They do react with water, and but not directly with water. They do have a kind of reaction with water. For silicon and lead and tin to react with water, the water must be in its gaseous state, that is, it must be steam, and of course the silicon or the tin must be red hot. So it must be very hot, and when they react with water, they form the oxide of water, the oxide of their element, and they liberate the hydrogen gas. Of course, lead also reacts with water. When lead is allowed to stay in water in an aerated position, it forms lead 2 oxide. Lead 2 oxide has PbO. It forms lead 2 oxide. And also when you burn silicon, carbon, and tin, if you burn them in the presence of excess air, you also have their oxides of 4. There are 4 oxides. So that's about everything for group 4 elements. The notable elements in group 5 are potassium and the notable elements in group 5 are nitrogen and phosphorus. Nitrogen and phosphorus. These particular elements do have two different oxidation states. The first oxidizing state is +3, while the other one is +5. So they can actually oxidize at +3 or at +5, unlike the group 4 elements, which have oxidation states of +2 and +4. So these particular elements, both nitrogen and phosphorus, they have oxides. They react with oxygen to form the oxides of 3s and the oxides of 5. They also react with hydrogen to form their hydrides. Their hydrides are identical, and also they react with chlorine to form their chlorides. So if you take note, you observe that we have N2O3. That's a dinitrogen 3 oxide, and we have P4O6. That's phosphorus 3 oxide. Yes, it seems like they are different from each other, but if you observe, it's just like this one is like 2 of this. So that's in the state in which they do exist. They have parallel characteristics. They have similar characteristics, but exist in parallel dimensions. So the same thing applies to the oxide of their fifths, of their 5. That's the +5 oxidation states. We have N2O5 and we have P4O10. So these are the ways in which this particular element, this particular group, do react. They have two different oxidation states, that's +3 and +5. They react with oxygen. They burn in air, and when they burn in air, all their oxides are acidic. All their oxides are acidic. So their oxides dissolve in water to form acids, basically. So their oxides are acidic anhydrides, and their hydride states exist in NH3, which is known as ammonia, or pH3, and also their chloride NCl3 or PCl3. Coming to group 6 elements, we have the common ones are sulfur and oxygen. Group 6 elements naturally exist in oxidation states of -2. They want to gain electrons. They are electron acceptors. They want to accept electrons. They are always seeking an opportunity to snatch electrons from people. So we find them in -2, and we see them reacting with especially alkaline earth metals with ease. When you burn magnesium in air, you have your magnesium oxide. You see this one loses 2 electrons, that's 2+, and this one gains 2 electrons, that's 2-. And of course, when you react sulfur with iron as well, the same thing happens. Iron loses electron to become 2+, while the sulfur gains electrons to become 2-. Now, it is also good to note that oxygen is slightly soluble in air, in water, while sodium is completely sulfur is completely insoluble in water. Oxygen is slightly soluble in water, sulfur is completely insoluble in water. Of course, when they react with hydrogen to form their hydride state, oxygen reacts with hydrogen to form water, while sulfur reacts with hydrogen to form hydrogen sulfide. So we have come to group 7 elements. Group 7 elements are interesting elements. They are described as the halogene family, and they are made up of elements they are univalent in structure. They are negative univalent in structure, so which means they always carry a -1 around. They carry a -1 electron. They have 7 electrons in the outermost shell, and this naturally makes them ready acceptors. They react with metals easily in electrovalent bonds. Reaction with metals is always with electrovalent bonds. They exist in diatomic structure. They exist in diatomic structure, and in this particular group, you have elements as fluorine, chlorine, bromine, iodine, and iodine. Yes, iodine. You have fluorine, chlorine, bromine, and iodine. So, how do these particular elements react? How do they behave generally? Generally, we'll find out that they are all non-metals. They are all diatomic. They have colors. They have colors. They are colored elements, and they are hydrides dissolve in water to produce strong acids. The hydrides dissolve in water to produce acids. Also, the progression, they move from, if you're moving from fluorine to chlorine, fluorine is a gas, chlorine is also a gas, bromine is actually a liquid, and iodine is solid. So, and of course, there are colors. Fluorine is yellow, bright yellow, chlorine is greenish yellow, bromine is reddish brown, and iodine is black in color. These are the halogen family. We call them the halogen. And why do we call them the halogen? We call them halogens because they are the ones that are described as the salt formers. The word halogen means salt forming. So they are elements which actually are responsible for the production of the salts, major salts. When you react them with solid metals, other metals, alkaline metals, or alkali earth metals, they produce salts. They produce different kinds of salts. And of course, yes, I have this particular description on the board. They also engage in displacement reactions. Displacement reactions, and the displacements always follow this particular order. Fluorine can displace chlorine because it is higher, it is more electronegative than chlorine. We're talking about electronegativity later in this lesson. But fluorine can displace chlorine, while chlorine can displace bromine. Bromine can displace iodine. Iodine cannot displace bromine. Bromine cannot displace chlorine. Chlorine cannot displace fluorine. Fluorine can displace iodine. Fluorine can displace, and vice versa, based on their positions in the electrochemical series. Okay. So let's talk about the group 0 elements. The group 0 elements are known as noble gases, or oftentimes called the rare gases. They make up for about 1% of the atmosphere, the Earth's atmosphere, and that is a mixture of gases in the air. We have them listed as helium, the neon, the argon, the krypton, the xenon, and radon. So all these elements have their outermost shell filled up completely. Helium has 2, neon has 2,8, argon is 2,8,8, krypton is 2,8,18,8, xenon is 2,8,18,18,8, and radon having 2,18,32,18,8. We see these particular electrons, all of them have their outermost shell completely stacked, completely filled up. So because of the complete filling up of their outermost electrons, outermost shell, they do not partake in any chemical reactions. They do not partake in any chemical reactions. They do not partake because they are already stable. They have no electrons to lose, they have no electrons to get. But they are used in chemical reactions either as reagents, catalysts, and the likes. So we use them in making of our bulbs, halogen bulbs. We use them in some of our other productions as such. So that's about the group 0 elements. So let's talk about the transition elements. Most people describe them simply as transition metals. Yes, because they are all made up. They are made up of a whole lot of group of metals. Why do we describe them as transition elements? They do behave in a mischievous manner. they do actually change in their appearance. They have a tendency of behaving one way in a particular situation and another in another situation. So we have them. They are actually, you can locate them between the group 2 and the group 3 elements. They do not fall under the normal classification of groups. So we created a special group for them and we call them the transition elements. But even inside the transition elements, we get to when we get to period 6. Yes, in period 6 we have a particular special group that we call the Londonites. So these Londonites actually are natural. They are very, very, very rare elements. I'll talk about some transition elements. Some of them are quite common. Some of them are not so common. Transition elements, we find elements like gold, like silver, mercury. We find them in all these transition elements. Copper, and many more. So, how about the Londonites? We find elements that fall between londonite, londinium, and lutetium. Yes, londinium and lutetium. They are rare elements. They are difficult to find on the earth. Also, we have the actinides. The actinides are special elements. They are artificial elements. Most of them are created in the laboratory. We find elements like between actinium and lawrencium. Among these elements, we also see that we have uranium among them. Yes, uranium actually exists somehow in nature, but it also can be described as an artificial element because of the rate at which it decomposes. Most of these elements in this group decompose. You have polonium and many of them like that. So in our future lesson, we will take our time to discuss these particular elements at a greater detail. So in this particular lesson, we've looked at the periodic table and considered the family of elements. We talked about the periodic table, then we looked at electronic configuration, groups and periods. We talked about periodicity of some properties. Then we considered each of the groups, that is group 1 through group 7 and group 0. And also we talked about the transition elements. So I haven't spoken about all of this in this particular lesson. In a few seconds, some questions will be displayed on your screen. Please attempt them. And if there is any of these questions that is proving to be challenging, you can go over the video one more time for clarity, for clarification. Thank you.